My name is Acep from Engineering Department of PJB Indonesia. Today I am going to present natural frequency evaluation of last stage to steam turbine blade power plant using finite element method. So electric power system must be able to provide electricity to customer with practically constant frequency. Frequency deviation from the nominal value must always be within allowable tolerance range. So the nominal frequency used in Indonesia is 50 Hz. At the frequency 47.5 it is Hz, it is expected that the generating unit will at least be able to last 30 minutes connected to the grid. But this is danger for turbine part. With the development trend toward high perimeter, large capacity, large stack LP blade become long and thin. The existing force on steam turbine blade increase significantly. The blade vibrates intensively and it is prone to high cycle fatigue. An effective way is to adopt an integral throat and lashing wire in the design of the blade to improve the rigidity and damping of the system. In this study, we will verify the possibility of the last stack low pressure steam turbine blade operating at their natural frequency, whether this is caused or the broken lashing wire. Model analysis was performed for low pressure last stack blade turbine on the 1 blade system and 5 blade system using ANSYS 2019 R2. This is steam turbine we are analyzed. Speed is 3000 rpm, length of the last stack blade is 900 mm. Blade material is 17 and 4 pH. Lashing wire is 15.5 pH. So the break of lash wire was driven by continued impact of the tugwell, lash wire and stoop, according to Xiao and Frankie at 2019. Or from the other table, while the type of lash wire that is welded directly to the blade, high stress concentration occur at the point which also trigger crack initiation. This is mentioned by both Sawaidi A and Mohammadi Arhadi 2010. Both sources of failure reference conclude that the failure mechanism is from the mechanism of fatigue. So we will check that under low frequency this is trigger fatigue failure or not. Methodology used is modal analysis was performed for low pressure last stack blade turbine on the 1 blade system and 5 blade system. Modal analysis is an analysis used to determine the vibration potential possessed by the low pressure turbine structure that is influenced by material and geometry. 1 blade system represents as freestanding blade, and software specification used to do the analysis is ANSYS 2090 R2 model. So this is block diagram. Geometry model, then a mesh setup, model simulation, natural frequency vibration mode analysis, 1 blade and 5 blade system. So this is the result for meshing setup. Method is hex dominant for 1 blade and 5 blade. Lash wire sweep. Blade body and face is 8 mm. So this is how we set up to do modal analysis. The root is set as a fixed support and zero displacement is given on the blade base. In short, the last stage blade construction is assumed not to do under deflection when operating. The connection between lash wire here and the blade is modeled as no separation contact because the loss frictional model will cause nonlinear calculation and cause the last wire and blade to penetrate each other on the simulation result. This is result compare actual measurement using CSI, pump test, and this is the modal analysis result 1 blade and 5 blade system. Here we can see for 1 blade system, modal analysis using pump test, difference is 3.7%. As we can see here, for 1 blade system, natural frequency first is 190. This is for first frequency with the actual measurement using CSI, so 202 and 200. This is the result modal analysis for 1 blade system. Natural frequency first, second, third, fourth, fifth, and sixth. So we plotted result on the CAMPBELL diagram with the different RPM of steam turbine. So we got intersection of natural frequency first and second and third. This is intersection, this is dangerous area. So this we got the intersection and 1 time, 2 time, and 6 time with the critical speed for the last blade is 2639, 2915, and 2783 for 1 blade system. And this is the result for 5 blade system, modal analysis, natural frequency, first, second, third, fourth, fifth, and sixth. We also plot the model for 5 blade system. This is the intersection, the dangerous area where operation under low frequency. This intersection is critical speed mode 2 and critical speed mode 3. So we got RPM is 2548 and 2563 at the 3 time and 5 time excitation frequency ratio. So the conclusion is, based on the model analysis evaluation using finite element for the 1 blade system, natural frequency mode 1 is at 2639.6 RPM or 43.99 Hz. Mode 2 at 2915.2 RPM or 48.59 Hz, and mode 3 at 2783 RPM or 46.38 Hz. If there are too much looseness on the shorts and damping wire, so that the blade operates as if it is as a freestanding blade, then it is very dangerous, causing by intersection second modes at 2915.2 RPM when the grid system is frequency low. This is a 1 blade system without the lacing wire. For 5 blades and laced wire system, there are 2 critical speed value. Vibration mode 2 at 258 to 2548.4 RPM or 42.47 Hz. Vibration mode 3 at the end vibration mode 3 at 2563.1 RPM or 42.76 71 hertz. So this is not in the limit of low frequency, because the limit of low frequency that unit expected connected to the grid is 47.5. This is safe because this is in the area below the limit low frequency of the system. So that integral should let and damping wire increase stiffness and cause it is to operate more safely when the frequency of the grid drop below nominal frequency 50 MHz and the limit is 47.5. It can be concluded that the setting under frequency is not the range of natural frequency elastic low pressure turbine blade, and the lashing wire damage is not triggered by natural frequency steam turbine blade. Thank you.